Welcome to our deep dive into earthquake engineering, a field dedicated to understanding and mitigating the risks posed by earthquakes. In this video, we'll explore the science behind earthquakes, the types of hazards they present, and the engineering strategies used to reduce their impact. Whether you live in an earthquake-prone region or are simply curious about how modern society prepares for these natural disasters, this journey will offer valuable insight. Let's begin by setting the stage for why earthquake engineering is so crucial in our world today. Before we dive into the details, let's outline the main goals of this lecture. By the end, you'll be able to compare different strategies for dealing with earthquake hazards, describe the factors that influence earthquake damage, identify which hazards can be mitigated through engineering or planning, and recognize how socioeconomic factors can limit mitigation efforts. These objectives will guide our exploration and help you understand both the science and the societal aspects of earthquake engineering. One of the most pressing concerns for residents of southern British Columbia is the potential for a megaquake, often referred to as the Big One. Evidence for such an event comes from seismic gaps, tectonic settings, geological records, Japanese sea level data, and indigenous oral histories. Despite no major earthquakes since European settlement, the region's tectonic setting suggests that a significant event is not just possible but likely. The question is if but when. Megathrust earthquakes occur when a young, buoyant oceanic plate subducts beneath a continental plate, increasing friction and strain. In Cascadia, the interval between such quakes averages 500 years but can vary widely. Historical records are limited, so scientists rely on geological evidence and indigenous accounts. Notably, Japanese tsunami records from 1700 point to a massive earthquake in the region, highlighting the global impact of these events. Vancouver faces several types of earthquakes: megathrust events every few centuries, shallow earthquakes that can reach magnitude 7, deeper quakes up to magnitude 8, and regular but small episodic tremor and slip events. Each type presents unique challenges for engineers and emergency planners, requiring tailored strategies for risk reduction and preparedness. British Columbia has experienced several significant earthquakes in its history. These past events serve as important case studies for understanding the region's seismic risk and for improving engineering practices. By analyzing the damage and response to previous quakes, engineers can develop better strategies to protect communities in the future. Preparedness starts at home. Many people take steps such as assembling earthquake kits, securing heavy furniture, and learning about local risks and emergency procedures. These actions, while simple, can make a significant difference in reducing injury and loss during an earthquake. Community surveys often reveal a range of preparedness levels, highlighting the need for ongoing education and outreach. There are two main strategies for managing earthquake hazards: empirical and early warning. Empirical strategies involve setting construction standards, evaluating insurance risk, and choosing safe sites for critical infrastructure. Early warning systems aim to provide alerts before shaking starts, giving people and systems precious seconds to take protective action. Both approaches are essential for reducing the impact of earthquakes. Probability analysis helps determine the likelihood of an earthquake of a certain intensity occurring at a specific location. This method relies on historical data, including the frequency, magnitude, and spatial distribution of past earthquakes. By understanding these patterns, engineers and planners can better assess risk and prioritize mitigation efforts in vulnerable areas. Occurrence rates estimate the probability that an earthquake of a given magnitude will occur within a certain period. For example, the San Andreas Fault in California was quiet for nearly 20 years before a magnitude 6 quake struck in 2004. These predictions help inform building codes and emergency planning, but they are not foolproof due to the complex nature of seismic activity. While occurrence rates are useful, they assume a uniform distribution of earthquakes over time, which isn't always accurate. Historical records are often too short, and earthquakes can cluster in time or occur in unexpected gaps. In these seismic gaps, plates may be stuck, storing strain energy that could be released in a major event. Understanding these limitations is key to improving risk assessment. Seismic gap is a section of a fault that has produced earthquakes in the past but is now quiet. Strain builds up in these gaps, increasing the likelihood of a large quake. For example, the Loma Prieta earthquake in 1989 occurred in a region that had been seismically quiet for decades. Monitoring these gaps is a critical part of earthquake hazard assessment. Throughout history, unusual animal behavior has been observed before earthquakes. Dogs barking, horses stamping, and even snakes emerging from hibernation have been reported as precursors. While intriguing, these observations are not reliable enough for scientific prediction. Still, they highlight the complex and sometimes mysterious ways in which nature responds to seismic activity. Modern early warning systems use a variety of methods to detect precursor events. These include monitoring foreshocks, changes in land shape, groundwater fluctuations, magnetic field variations, and radon gas emissions. Instruments like those used by the USGS in California provide valuable data, but predicting the exact timing and location of earthquakes remains a challenge. Today, the focus has shifted from predicting earthquakes to preventing catastrophic effects. This involves understanding hazard potential, population density, building design, and emergency response procedures. With over 40 countries at risk and hundreds of serious earthquakes each year, prevention strategies are more cost-effective and reliable than prediction alone. Major earthquakes pose a threat to over 40 countries worldwide. Each year, about 100 earthquakes are potentially serious, and a couple are considered major. The economic and human toll can be staggering, as seen in the 1999 Kobe earthquake in Japan and the 2001 Gujarat earthquake in India. These events underscore the importance of robust engineering and emergency planning. It's important to distinguish between hazard and risk. A hazard is a condition with the potential to cause harm, while risk measures the probability and severity of adverse effects. In earthquake engineering, risk is calculated as the product of hazard and probability. This framework helps prioritize resources and design strategies for maximum safety. Let's consider different risk scenarios: a large earthquake in a small town, a small quake near a nuclear plant, a rare but powerful quake in Vancouver, and a similar event in rural China. Each scenario involves different levels of risk based on population, infrastructure, and potential consequences. This exercise highlights the complexity of risk assessment in earthquake engineering. Amount of damage caused by an earthquake depends heavily on its magnitude and duration. Larger, longer-lasting earthquakes release more energy, causing greater destruction. Additionally, the distance from the earthquake's focus matters. The further away, the less intense the shaking. Understanding these factors is key to designing safer buildings and communities. Population density and time of day are critical social factors in earthquake damage. Densely populated areas face higher risks of injury and death, especially during working hours when many people are in large buildings. For example, a 6.4 magnitude earthquake in Turkey led to tragic losses when a school collapsed during the day. Geology of an area greatly influences earthquake damage. Stronger, older rocks transmit seismic waves more efficiently, while surface soils can amplify shaking. Buildings on solid bedrock generally fare better than those on loose or unconsolidated soils. This knowledge informs site selection and construction practices in earthquake-prone regions. Unconsolidated soils can amplify seismic waves, increasing the risk of damage. Ground amplification, differential settlement, and resonance effects all contribute to the severity of shaking. In some cases, saturated soils may even liquefy, further undermining the stability of buildings and infrastructure. The type of building construction plays a major role in earthquake vulnerability. Poorly supported bridges, unreinforced masonry, and buildings with weak connections are especially at risk. Modern engineering focuses on designs that can withstand shaking, prevent collapse, and minimize casualties. Ground motion is the primary cause of structural collapse during earthquakes. The shaking can cause columns to fail, buildings to topple, and bridges to disconnect. Notable examples include the 1994 Northridge earthquake and the 1995 Kobe earthquake, both of which caused significant structural failures and loss of life. Amplification and resonance can cause buildings to shake more violently during an earthquake. Unconsolidated soils increase the amplitude and duration of seismic waves, while buildings with certain heights or designs may resonate with the shaking, leading to greater damage. Understanding these effects is crucial for safe construction. Every building has a fundamental frequency based on its height, design, and materials. When the frequency of ground shaking matches a building's natural frequency, resonance occurs, leading to severe damage. Adjacent buildings with different frequencies can even collide, compounding the destruction. Modern earthquake engineering employs several techniques to protect structures. Bracing adds reinforcement against shearing and toppling, isolation separates buildings from ground movement, and damping absorbs seismic energy. These methods have proven effective, as seen in the Alaska pipeline, which withstood intense shaking during the 2002 Denali earthquake. Liquefaction occurs when saturated, loose soils lose their strength during shaking, behaving like a liquid. This can cause buildings and infrastructure to tilt, sink, or collapse. Areas with water-saturated, unconsolidated soils are especially vulnerable, making soil assessment a key part of earthquake engineering. A dramatic example of liquefaction occurred during the 1964 earthquake in Niigata, Japan. Large apartment buildings tipped over as the ground beneath them lost its strength. Such events highlight the importance of proper site selection and soil treatment in earthquake-prone areas. The Fraser Delta in British Columbia is underlain by deep, water-saturated, loose siltson deposits, making it highly susceptible to liquefaction. Areas built on fill, like False Creek, are particularly at risk. Understanding local geology is essential for safe urban development in such regions. Mitigating liquefaction often involves densifying loose, unconsolidated soils before construction. Techniques include dynamic compaction, vibroflotation, and compaction grouting. These methods strengthen the ground, reducing the risk of liquefaction and helping protect buildings and infrastructure from earthquake damage. Even moderate earthquakes can trigger landslides on susceptible slopes. Larger quakes may cause thousands of landslides, destabilizing slopes and leading to rock falls or massive earth movements. These secondary hazards can be as deadly as the initial shaking, especially in mountainous or hilly regions. Tsunamis are massive sea waves caused by the displacement of the sea floor during undersea earthquakes. These waves travel at high speeds and can reach heights of over 50 meters. As they approach shallow water, they slow down but grow in height, causing devastating flooding and destruction along coastlines. 2004 Indian Ocean earthquake with a magnitude of 9.1 generated a tsunami that killed approximately 275,000 people and displaced over 1 million. This disaster remains one of the deadliest in modern history, underscoring the need for early warning systems and coastal preparedness. When assessing earthquake hazards for different communities, it's important to identify not just the risk of shaking, but also secondary hazards like liquefaction, landslides, and tsunamis. Each community's geography and geology will determine its unique risk profile and the best mitigation strategies. Recent decades have seen significant economic and insured losses from earthquakes. The 1994 Northridge quake cost $21 billion in insured losses, while the 1995 Kobe earthquake resulted in $180 billion in economic losses. As urbanization increases, so does the potential for even greater losses in the future. Looking ahead, the trend of increasing urbanization and wealth concentration means that future earthquakes could result in even larger economic losses. For example, the next major Tokyo earthquake is expected to cause losses of up to $1.7 trillion. This highlights the urgent need for continued investment in earthquake engineering and risk reduction. Seismic hazard maps and risk maps are essential tools for siting and constructing buildings safely. These maps incorporate seismic frequency, probability, and geological conditions to guide decisions. Building codes based on these maps recommend bedrock foundations, symmetrical designs, and secure attachments for appliances and furniture. Effective emergency planning can greatly reduce the impact of earthquakes. This includes preparedness education, enforcement of building codes, emergency broadcasting, evacuation plans, response teams, and disease control. Supplies and disaster relief are also critical. While engineering solutions are vital, the human element must never be overlooked. Socioeconomic factors play a significant role in determining the extent of earthquake mitigation possible. Wealthier regions can invest more in engineering solutions and emergency planning, while poorer areas may struggle to implement even basic safety measures. Addressing these disparities is a key challenge for global earthquake risk reduction. To recap, earthquake engineering involves understanding hazards, assessing risks, and implementing strategies to reduce damage. Key factors include magnitude, geology, construction type, and social context. Both engineering and emergency planning are essential for minimizing losses and protecting lives. While much of earthquake engineering is technical, it's important to remember the human element. Community engagement, education, and resilience are as vital as any engineering solution. By working together, societies can better prepare for and recover from earthquakes. The field of earthquake engineering continues to evolve, with new technologies and materials offering improved protection. Innovations like smart sensors, advanced modeling, and resilient construction techniques are shaping the future of disaster mitigation. Staying informed and adaptable is key to ongoing safety. In summary, earthquake engineering is a multidisciplinary field that combines science, engineering, and social planning to reduce the risks and impacts of earthquakes. By understanding hazards, improving construction, and fostering community preparedness, we can build safer, more resilient societies. Thank you for joining us on this exploration of earthquake engineering.